5 minutes left to finish. Thank you.
Okay, so good morning and good afternoon to everyone. Thank you. First of all, thank you very much to the organizer for inviting me to this splendid conference. So thank you very much. It has been a few years that I have been trying to attend Iwara. This is for the first time that I'm be able to do it. So I'm very happy to be here with you. So today my talk is related to dark matter. So let's start. I would like first to mention the collaboration. The results of this talk have been recently published, and we will see in a moment, in a paper in collaboration with Carlos Arguelles, with Eduardo Becerra, Andreas Fruit, and Remor Fino. So is title of my presentation, A Crucial Test of the Fermionic Dark Matter Constituency of our galactic core from the geodesic motion of H2 and G2. So let's start. This is, here I will assume that dark matter is what its name tells us. So there is matter. So the view of this work is that general relativity is the theory of gravitation, and the correct theory of gravitation, and that dark matter is just made of some particles that we are trying to get some crucial information from galactic dynamics. So this is our general view, very simple actually, of dark matter content of a galaxy. So usually when we speak about dark matter, usually we refer to the dark matter halo actually, so to the outer parts of the galaxy, where we have information from the so-called rotation curve, so the velocity at which the stars and systems move around the galactic center. But what about the galactic center? So we have also a galactic core. So we have some matter inside. So what happened there? So what we were trying to answer is, what about the dark matter content toward the center of the galaxy? What is there? So as you know, we have, there are in the literature actually many phenomenological distribution of dark matter, phenomenological profile for the density, to describe the density of dark matter in the galaxy. Of course, in they are phenomenological, they are based on where data are. Data are from some point in the galaxy on, but what inside? So our approach is different. So since we don't want it only to know if the dark matter profile is a power law or exponential or whatever. So we would like also to know what is dark matter. So what is this particle? So this particle is a fermion, is a boson, is a sharp neutral, or what it is. So our view has been this. So first we will set, assume a nature for this dark matter particles, and then we move on. So now we would like to know what would be the distribution of dark matter from the center of the galaxy all the way to the outermost halo of the galaxy. So this was so far one of the first complete works on this theory. So this is on the core halo distribution of dark matter of galaxy. So it's a few years ago paper already. It's a bit now old, let's say 5 years, where we introduced this. So what is that? So first of all, we assume that the dark matter are fermions. So let's see what happens if dark matter are fermions. Why not? So they can be fermions, they can be boson, but let's assume that they are fermions. And they are fermions, and to calculate the distribution, of course, we have to set the equation to state. Of course, if they are fermions, so they have to satisfy the Fermi-Dirac distribution function. You know, the Fermi-Dirac distribution function have different regimes. So in the cold regime, you have the degenerate state of the fermions, while in the hotter regime, we will have just a classic Boltzmann distribution. So the issue is here, what is the state of these fermions in the galaxy? So to know this, we have to know how will be how the density, which is the density and temperature of these fermions in the galaxy from the center all the way to the halo. So to do that, we have to specify, to solve the hydrostatic equilibrium equations of this Fermion gas in the galaxy. So we'll have this Fermion equation of state plus equilibrium, gravitational equilibrium of these fermions in the galaxy. So we'll solve this in general relativistic equations, and of course this is hydrostatic equilibrium equations for this equation of state. Plus we have the Tolman and Klein thermodynamic equilibrium conditions. So the temperature, redshift temperature is constant throughout, and also the redshifted chemical potential of particles is constant throughout the system. And so we can proceed to solve that. And now it becomes clear what we call that the core halo distribution. So what we are showing, I'm showing to you here is the profile of the degeneracy parameter inside a galaxy. A galaxy is similar to the Milky Way. So for example, you see here is the mass of the particle in this column here. So the mass of the particle and different degeneracy parameter at the center, and you see how it goes from positive to negative, and some specific behavior. It means that toward the center of the object, the system becomes degenerate. Why as soon as you move to the outer parts of the galaxy, these fermions have to transit to the Boltzmann, to the classic regime, and you have an intermediate regime somewhere around zero chemical potential in transit from degeneracy to classic regime. But this is the degeneracy parameter. What about the density? So density distribution looks like this. So this is density, units of solar masses per cubic parsec as a function of the distance from the center. So you see here that this is, it looks similar to the degeneracy parameter. So there is a degenerate core. This we start to use this name, degenerate core, or degenerate quantum core, or high dense core of dark matter. So there is a big concentration of dark matter at the center. Then there is a drastic drop of the density, then there is a plateau, and then there is this very specific behavior. This is almost power law, becomes a power law behavior of the density with respect to the distance. And this is very important, this behavior in the outer halo. Why? So what happens if we make a plot of what would be the rotation curves for this kind of distribution. So you have the density distribution, you can reconstruct the mass profile, and with the mass profile, you can reconstruct all the rotation curves. So at the end, you get something like this. So you see that is the solid part. So this in the outer parts of the galaxy, it is plane what be the flatness of the rotation curves. So this is this part here. You can see the scale. This is 10 to the 4 parsec. This is 10 kiloparsec is here, and start to become flat. Then, as you enter in the regime of the degenerate core, you see it has some minimum here, and then it develops a second peak over here. And this is also a Keplerian regime. This is a Keplerian regime of this power law behavior here of the velocity curve. So this was our first work when we start to see that actually this kind of model could explain the flatness of the rotation curve. But even more interesting than that for us was the behavior, this of the occurrence of the existence of this degenerate core. So what happened with this core? How massive it is? So, and then after that, here is a bigger plot of this, and just a comparison with some phenomenological profiles. This is the Navarro-Kenyan white profile, is this one, and then this is a Nasco and Equalian profile. So this is just to compare how it compared with phenomenological profiles. So our question was, so it turns out this general picture, you have a high density general quantum core and a classic Boltzmann regime of these fermions in the halo. And so we are now to be concentrated a little bit more on this. What happened with this degenerate core? And our question was actually what we are going to show in a moment is that we were looking at the possibility that this degenerate core could actually replace the existence of the hypothesis that at the center of the galaxy there is a supermassive, massive black hole, a massive black hole of 4 million solar masses. So let's go bit by bit to that point. But before that, that was the first treatment of these fermions in the galaxy. There is an extension of that work that I'm presenting here, in which is I probably, if you see here the density profile, okay, this will continue. This density profile will continue roughly 1 over r squared all the way to infinity. But this is a very long result. But the final temperature Fermi gas is unbound. So you have to introduce a cutoff in the phase space of the Fermi distribution to introduce a finite size of the galaxy. So we made that in a second work of this. And so we have to introduce this cutoff energy cutoff parameter. And with that, these are just, we don't go into the details of that, of this case. This is what is important, is that the distribution function you can identify here is the energy cutoff. This will introduce the cutoff of the size of this related to the size of the galaxy. And this is these are the new, how this parameter changes the distribution of fermions, of these fermions in the galaxy. So you can see there are similar curves, similar but not the same as the previous one. And here again, these have for different masses and for different central degeneracy parameter. And here they are the corresponding rotation curve. Here you can see we are plotting also the data of the rotation curve and the total baryonic plus dark matter contribution to the velocity rotation curve is given by the red line. So the red line will be the result of the combined fitting of the fermionic dark matter plus the baryonic component, which are the green curves here. What you can see right away is that there are some curves like this is an example here as the yellow one. This corresponds to a fermion mass of 0.6 kiloelectron-volt that are ruled out already by the rotation curve, because you see it overshoots the data. So actually already here we could rule out some specific masses for this fermion, because as I mentioned at the beginning, we want to know what these fermions are. So supposed to impose, to get some limits on their measure. So here, actually, while performing this exercise of plotting the rotation curves, we could rule out all fermion masses below 10 keV. So all masses below 10 keV were ruled out. Second point. Then we talk. But what happened if we request to the core, to the dense core, to be as massive as 4 million solar masses, and its radius, you see that it has some radius here over here, and this radius happens at the peak of the rotation curve. What happens if we request to be as massive as that, at 4 million solar masses, and its radius not to be larger than the pericenter of the closest stars known to have a Keplerian behavior around the center of the galaxy. And these are the S-cluster stars that are plotted here. So if we request these two things together, we rule out all masses below 48 keV. Okay, so below 48 keV, you cannot explain these stars here, the S-cluster, the velocity of the S-cluster stars and the rotation curves of the outer halo of the galaxy. There is a second, that would be a lower limit for the fermion mass. There is an upper limit that you see here, about 345 keV, that corresponds, since we are speaking about, I mentioned to you, that the fermion gas is degenerated at the center. So as you remember, this classic result that everybody knows, that when you have a gravitating system of degenerate fermions, there is a critical mass for gravitational collapse. So when you impose that core to be 4 times 4 million solar masses, for a mass of 345 keV, that core is unstable for gravitational collapse. So these are the two limits that we get in this work. This is just a zoom of the outer head of the galaxy, where we show the feet of the rotation field. So it happens, this gravitational collapse. So this gravitational collapse should happen for this critical mass, and so I will come back to this point after. This is a channel for, so this will be a channel for black hole formation. So, but what kind of black holes this collapse of dark matter cores would form? So this is a question that depends specifically on which is the mass of the fermion. Because as you remember, the critical mass for a self-gravitating system of the fermions goes as sorry for the typo, it's a Planck mass cube over fermion mass square. So I put already, so there is no minus here. So it is inverse proportional to the square of the fermion mass. So which is the fermion mass is a key point to know which are the massive black holes that this collapse, the collapse of dark matter cores form. So let's go ahead. So this could be, in fact, a channel for the formation of the supermassive black holes that are observed in a galactic nuclei, for example, in NEP7. So it can be black hole seeds, actually. So let me come back to this point after. We extend that work to other galaxy types, and not only to the Milky Way, but also to elliptical, deep elliptical, and to dwarf galaxies. So we perform this kind of work. This is reference. So I will jump some of this. This is just some comparison with existing phenomenological relations in the literature, for example, between the total mass of galaxies and the mass of the dark objects at the center of the galaxy. We perform this theoretical work for fermions and compare with the data. So this is the so-called Ferrarese relation that are this strip over here, and we show that effective. That in fact you can find the set of parameters of the fermion that can fit that, and we do that for 48 keV in this work. This is another relation related with the so-called surface density inversor relation. This is made for 48 keV, so this will be the density. This is the surface density, solar masses per parsec square. This is just to be more clear, is more or less the density that you have around this part of the galaxy. As a function, this is for different galaxies. It seems to be similar. So this is a Donato relation. So we do that also for fermions. We show that this, in fact, it is also consistent for fermions, so for the AKB. But let's now come to this to the latest work on this. So I mentioned that we were trying to explain with the dark matter core the motion, so the velocity of the S-cluster stars. But we made that, let's say, in a superficial way at the beginning, just to show that it could happen, it could be the case. But then we moved to a more specific calculation. Let's say take specific sources or specific stars, some of them, and compute accurately the motion in the field of the dark matter, of this dark matter, and in the field of a black hole, and let's compare the two models. So specifically, we use in this case the S2 star and the G2 cloud. It just appeared just a few days ago in Astrophysics. It was published in September 4. So really just this week, and the idea was to recover what is the motion, mean position, and the velocity from the theoretical point of view and compare with data. So what is the point? Why S2? S2 is probably the most known star near the galactic center. It has a period, orbital period of about, let's see, of about 16 years. It's relatively close. I say relatively because actually, if you assume that the galactic center has a mass of 4 million solar masses, it would be the pericenter of S2 is about 1,500 solar radius, which is actually not so close. And this is one of the reasons why we move ahead with an alternative scenario for the supermassive black hole, because actually this evidence for from the motion of the stars is, and you have the evidence from a black hole at 1,500 radii is actually not very good. So, so there is a...
Jorge, sorry, there are 4 minutes left.
Okay, thank you. Oh, thank you, that's good. Okay, so that's why we move ahead with with alternative scenario. What about G2? G2 is a cloud that challenged the scenario of a massive black hole, because actually it had been shown that the observed motion of the body after its passage from the pericenter, after its pericenter passage cannot be explained with the clear motion of the cloud around a massive black hole. So this is just a technical details of how to reconstruct the orbit of the object in the field of the dark matter. So this is just a detail. I will not stop here. I will go directly to the result. This is how did you get parameters of the model through the effective potential. These are the parameters. So we reconstruct the parameters for S2 and for G2. RAR, probably I did not stop there, but this means the Rueda. This is referred to the fermionic dark matter model, and this is DH for black hole, for the central black hole hypothesis. So we reconstruct what would be the best fit for this and compute the reduced chi-square for position and velocity. So this Z here is not Z position, but this is from redshift. So measure redshift. So actually from the line of sight radial velocity of the system. What we found is that for S2, actually the fit, the distribution of dark matter fits better the data for the S2. In the case of G2, we show actually for G2 the data of the position is not very good. So we have to look only of the radial velocity. I will show the plots in a moment. And actually also in the case of G2, these two, the dark matter distribution can explain the motion of G2. Just to mention the case of black hole, the motion of G2 is this lower velocity of G2 after the post pericenter passage is explained by introducing a friction force by an accretion disk. In the case of a black hole, here is only geodesic motion. So these are summary of the plots of the fits. So this is the orbit of S2. So you have position, X position, Y position. These are just ray ascension and declination of the position, angular position, and you make this your theoretical model, and this is the redshift function that fits in the two models. So the red model is the red is the dark matter model, and the blue is the black hole model. So you can see even by eye how good the fits are. In this case of S2, the two models are comparable, although the dark matter distribution is slightly preferable. This is what is called the redshift excess. So just that to show that general relativity is essential to explain this. I mean, how the deviation from the purely Newtonian motion. And you can make the same for G2. And again, and you can see here more representative the fit of the redshift function, so the radial velocity, that the red one, only the red one can fit the post pericenter passage. You got this 3 point and not the blue one. So these are other words that we just make about fermionic dark matter. We will not stop there, but this I can. This is my final slide. Conclusion of this discussion. The case of high quality data allows to test alternative to the central black hole at the center in our galaxy. Fermionic dark matter have this core halo profile, that can, in which this core can mimic this black hole. And the data of G2 challenge the black hole scenario, so allow also to test additional scenario. So results at the gravitational field of the fermionic dark matter model explain the motion of the nearest objects, and also, as I showed you in previous work, also of the rotation field of the galaxy. And this A in particular is 22 are better explained by the best score of dark matter. For a fermion mass, this is important. We made the fit for 56 keV fermions. So this is the important point. And for this value of the mass, the core of dark matter collapses to a black hole of when this core has 100 million solar mass. So these 100 million solar masses could be seed black holes for the supermassive black holes observed in active galactic nuclei. That's all. Thank you.
Thank you for your nice talk. So I asked Beno if we have any questions in the Q&A
Yes, we have two
chat.
questions.
Excellent.
The first question is from Renxing Xu. Jorge introduces temperature in the calculation. Does this mean dark matter is self-interacting so that the dark matter particles are thermalized?
Yes, thank you. This is an important point. Yes, in this model, dark matter is at finite temperature. So here the point is we are assuming we have some hypotheses in between this hypothesis that is thermodynamic equilibrium of this fermion at this moment to explain this galaxy. So it remains to explain the evolution of the galaxy formation and the evolution of dark matter, how these dark matter fermions get thermalized. And so probably there are mechanisms which can explain that, but that's a different story, but this is correct. We have some additional works about the self-interactions of dark matter, in which we have this in particular. Let me find this in this list. Is this one? The self-interaction is this article 2017, in which we introduce self-interaction between fermions and put some constraints to the coupling constant, assuming that there is just this mediated by a boson exchange.
Okay, thanks for the answer. The second question is of Rafael Rias. For gas to collapse, we know that it is the Jeans mass, more sensitive to gas temperature, that determines the critical mass. So when you say the Planck mass controls the critical mass for dark matter to collapse and provides channel for black hole formation, then which parameter this Planck mass is more sensitive to?
Okay. Here, yes, it's different. It's not the Jeans mass. Here is just is the analog of Chandrasekhar mass. So it's for degenerate, for the core is degenerate, is not sensitive to temperature effects. Only thing it is sensitive to temperature effect is the halo of the galaxy, not the core. So the core can be considered as cold, in the cold regime, so at zero temperature regime. So in that case, the critical mass for gravitational collapse is proportional to the cube of the Planck mass, and inversely proportional to the square of the fermion mass only. Of course, there is some constant of order unity inside, in front. The Planck mass is the square root of h bar c over g. So it's only the fermion mass which determines which is the mass of the core, of the unstable core, and the fundamental constants giving the Planck mass.
Okay, thanks for your answers. There are no more questions now.
Excellent. Thank you. So let's thank our speaker again.
Thank you, Jorge.
Thank you.
So we have our next speaker, Dr. Rota Rosinska.